Hello and welcome back to Calculus 1. It's one of my favorite sections, applied section on related rates. Related rates. So first off, note it's plural, right? So we're going to have multiple rates in one formula, and they will be related with whatever else is there. So if you observe some kind of, let's say, metal plate that it's left on the, that is exposed to heat, let's say, that metal plate is going to expand. So side A will grow into side A1, and then area A will also grow into some A1. So if this is a square, A and A, I know that area is equal to A squared, side squared. And if I want to see how fast the quantity is changing, I will take the time derivative. Let's write that in blood. We take the time derivative to measure how fast a particular concept changes in time. So I will take the time derivative here, and that's d dt. Note the use of implicit differentiation now. We have dA dt is equal to the derivative of a squared is 2a, and then we follow with a dA dt because the variables did not match. So note that you have two rates. The rate of change of area in time and the rate of change of length of the side in time. And they are related with this 2a in between. So dA is the rate of change of area in time, and here in blue the rate of change of the length of the side. In time. So if I know one of these rates, I can calculate the other. It's very Very simple, very straightforward. The problem in the book has an oil rig which had some oil spill into the ocean. So now you have these concentric circles of polluted water that are growing in time. So you see that as radius r grows in time, the surface area of the contaminated water, right, with oil also grows in time. And you can calculate how fast is that area changing at every time. So you know that area of the circle is pi r squared. If you want to study the change in time, you hit this with the time derivative. So now the change of area in time, because everything changes with time, there's no instantaneous anything. So the change of area in time is 2 pi r dr dt. Usually you forget this and then it's mess. Related rates. You have to have at least 2. You can have 3 or more, but at least 2. And there it is. We're done. That's it. You're supposed to find this formula. If you have numbers, you plug numbers in, you come up with the answer. So the job in this section is for you guys to figure out what geometry is there. Is it a square? Is it a circle? Or is it some kind of 3D object? I mean, have that as well. Volume of a cube or a ball or something will change. Well, we'll see all of those problems, obviously. So the whole idea is to learn how fast is something changing. Because clearly, if the area of this oil spill is changing quickly, meaning grows quickly, the sooner you get the cleanup crew and everything situated, the better. Because you will just be cleaning larger and larger area as you prolong the cleanup. So we have. So what we do here is with the growth of the radius, it's common sense that the area, the contaminated area, is going to grow as well. This problem is done in the book, and they actually give you some numbers, I think. Yes, they say figure out how fast is the area growing if the rate of increase of radius is 30 meters per hour when the radius is 100 meters. So when radius is 100 meters, you have the growth of 30 meters per hour for the radius. You can actually calculate. So here we go. dr dt is given as 30 meters per hour. Please note the units. You see how units make sense? You have the radius, which is measured in meters, and you have time that it's measured in hours. Are we agreeing on that? So every time you have, when you have this type of a variable of the unit, something divided by something, that better be a rate. And clearly we have those done in time. So hours, months, seconds, whatever it is, unit of time that you are using. And then also say when radius is 100. So all I need to do is to plug in the change of area in time is 2 times pi times 100 times 30 equals to, that's 6,000 pi, right? Oh, meters squared per hour. So 6,000, and we put the correct units. Now this is roughly 18,000. Right, pi is close to 3. 3 times 6,000 is about 18,000. So about 20,000, whatever. 20,000 meters squared per hour. It's actually a lot. We know that we use rates to find velocities, right? Do we? We do. So here's another problem. We have two airplanes. Going towards the airport, and note that there is distance x for the top plane, and there is distance y for the bottom plane, and what we are interested in is the change in distance in time between the two airplanes. You don't want that distance to be 0, right? Not good. You also want to know how quickly they're closing in on each other. So how would you find the rate of change of distance between the two planes? Well, you look at the geometry first. So what kind of geometry do you have? Right triangle. Good. So we have right triangle. Now, as soon as you have right triangle, that means a lot of special formulas work here. Pythagorean theorem being one of them. So we see that we can write that x squared plus y squared is equal to capital D squared. Because we have distance in x. Let's say the airplane is 100 miles away. Distance in y, let's say 70 miles away, right? And then we also need, well, we'll see what else we need. So now, I wrote down the formula. See, the amount of formulas for triangle is finite. What can you have? Perimeter, area, if it's a right triangle, Pythagorean theorem, and then 6 trigonometric functions to write with opposite, adjacent, and so on, right? Yeah. So now we have just 9. Well, if you compress all of your trig into a single idea, right? You don't have too many options. Do we need the perimeter? No. Do I need the area? No. But I need to relate x, y, and d. The red distance here is capital D. That's the distance between two planes. So now, if I want to see how quickly these planes are coming together, I will take the time derivative of this. Time derivative is simply 2x dx dt, because we took the derivative of x in respect to t, plus 2y dy dt, because we took the derivative of y in respect to t. When variables don't match, you have to follow with the chain. We did this last time. And then 2d, the derivative of d squared is 2d, and then we have dd dt. All of these 2's drop, and the formula becomes x dx dt plus y dy dt equals to d dd dt. This is your mathematical model over here. As a mathematician, you can just walk away at this point because problem is solved. But you're engineers, so you want a little bit more. But you want to understand this, because if this means nothing, it's garbage. So what do we have? If you're looking at this formula, what do we have? What is x? Say it loud, air conditioning. What is x? Thank you. Distance of this plane from the airport. And what's dx dt? So what is that? The velocity, the speed. This is how fast the airplane, this is how far it has to go, and this is how fast it's going. You have the same thing happening here. The distance of the plane y and how fast that plane is going. And now you have the distance between the two planes and how quickly that distance is closing. Observe that this plane is going up on my diagram, so it's positive. And this one is going to the left. Positive is to the right. The distance between airplanes should be closing. This should be negative number here, right? If the planes are going towards each other, then you wait a little bit, the planes will be here, and that distance will be shorter. So, as you are looking at this, right, you see where you start creating the software that would do what? What do you get to create? I think there's a Joe in control tower trying to figure out where the airplane is. There's 13,426 commercial airplanes. This doesn't include any of the government stuff, any of the military planes, any of the cargo, FedEx and all. This is just passengers. And this is just United States. If you write a computer this is your computer science, all right? You write this thing, and it takes time to load all of it, but yeah. It's tracking live. Right, any flight, you just pick. And it tells you exactly where it's going, where it originated, and so on. If you get the subscription, they have also onboard cameras and stuff, so you can see the... But anyway, here it is. You just, random plane gives you everything for that plane. The trajectory, left, going. And this is, as I said, this is live. So you can trace any plane live as it goes. And it's the whole world. You can see the paths they take, right, everywhere. what have I done in the class over there? There was two planes coming up to the same airport, right? So, yeah, you have to figure out how to make sense out of all of this, right? And get all of that working. Yeah, total 13,436 airplanes in air right now. So going back to the United States, there we go. Zoom in. Zoom in. Wait for it to load. That's what it looks like. So, yeah, you gotta make sense out of this, right? So you write the code that traces all of these, and then we go back to our problem, which is that. And you have how far these planes are from the airport, and how fast each one of those is going, and then the distance between the two planes and how fast the distance between them is closing, making sure that that capital D doesn't go to 0, right? Because that's not good. So now, if you tell me that your airplane is going 600 miles per hour, well, that's going to be 600. If this one is going negative 480 miles per hour, because it goes to the left of its velocity, so negative over here, right? We get to calculate exactly the distance, we get to calculate exactly how fast the distance is closing, and obviously given that you give this calculation to the computer, right, the computer can maintain this calculation at all times and then notify you if there are issues, the planes are too close, or, you know, any of those things. This is what you are doing as a computer science, right? You're programming the software that it's going to take all of the responsibility of hand calculations away from, right, someone who might be distracted for whatever reason while they're doing the calculations. So with any type of numbers given, right, we can figure out. So two small planes approach an airport, one flying due west at 120 miles, and the other one due north at 150. So this one is 150 miles per hour. This is it done in a book. So 150 miles per hour, and this is 200. No, 120 miles per hour. Fly the same constant elevation. How fast the distance between the planes changing when the westbound plane is 180 miles. So 180 m. And the other airplane is 225 miles. Well, you can calculate D actually immediately using basic Pythagorean theorem. And then you have this, 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 and you can calculate how fast the distance is closing or changing at that point. So what do? We do the Pythagorean theorem immediately. 225 squared plus 180 squared is equal to D squared. And then you have your D immediately. Square root of 225 squared plus 180 squared square root, so 288.14 miles. So that's the current distance at the moment when we are looking at the how fast it's changing. So okay, so now my x is negative 120 times the distance is 180 plus the distance for this is 225 times the speed up is 150 is equal to d 288.14 dd dt, which is the change. And as you can see, I have all of these numbers, so just compute. I don't like that I'm getting the positive dd/dt, because the dd/dt should be decreasing. See, if you get negative dd/dt, that means that the distance is decreasing. Great, because it has a negative rate. But if you get the dd/dt to be positive, that means that the distance between the planes is growing, right? The positive change meaning you're adding distance. Negative change means you're closing the distance. So without calculating, I see this is wrong because this number is smaller than that number, so the sum of this is positive divided by the positive here will keep everything positive, and I don't like it. So let me read one more time. Two small planes approach an airport, one flying due west at 120, the other one flying due north at 150. Assuming they fly at the same constant elevation, how fast is the distance between the planes changing when the westbound plane is 180 miles from airport and the northbound plane is 225? Okay, so what is the issue here? Oh, it's going towards the airport, so that distance is okay. So this rate is also, so all of these rates are negative. This is a negative rate and this is a negative rate because they're going towards the airport. They're both decreasing the distance towards our reference point. Our reference point is here. This is where the airport is, right? They're going to land there. So you have the negative rates on both of them because they're both getting closer and they are covering this distance, making the distance smaller. So now all of this is going to be, all of this is now going to make sense. Good. So what do we have? We have 180 times 120 plus 225 times 150 divided by 288.14. Everything is negative, so the distance in time is approximately negative 192.1 miles per hour. No. Yeah, miles per hour. So that's how fast the distance is changing, and this is only at the values that are given to us. Nice. Another problem that you can consider would be an ice cube. Ice cube with a side A. Now cube has all sides the same, and we want to study the change in volume. If you leave the ice cube out on the sun, it's going to melt. What happens as the ice cube melts? What happens with the qualities of that cube? What's happening with length of the side? What happens with the surface area? What happens with the volume? Yes? They're all shrinking, right? So you are expecting a negative change in volume. So change in volume, dV dt. So first we write the formula that the volume is A cubed. That's the standard formula for figuring out the volume of the object, that it's like a box or whatever. X, Y, Z, right? Or A cubed for the cube. So now we're taking a time derivative. And when we take the time derivative, we get dV dt is equal to 3a squared dA dt. As soon as you get mathematical model, it becomes clear what are the values that you need. So you need to know how fast the size, the side is changing, which is something you can measure. And then you can also measure the current side. So these two numbers you can obtain. And once you have those numbers, you can compute the volume, the change in volume. Yeah. So we can come up with whatever values, doesn't matter. So let's say that change in length so change in length in respect to time. And that will be dA dt. You see, length is one-dimensional, right? If length is one-dimensional, well, then your A, right, is just going to have the units of length, and then divided by time, whatever they have. So let's see, what do we have? Let's say that dA dt is given as, since this is volume and it's shrinking, we should have a negative change, because we are losing volume in time. Losing the length side, the length of a side with the edge. So we have dA dt, just whatever number. Let's say it's changing by 0.1, whatever. When A is equal to, and how big is the ice cube? I don't know. How much is the ice cube? 0. That doesn't matter. 0.7. Whatever. What are the units here? Maybe inches, and inches per time, which is inches per, I don't know, hour, whatever. So now all you need to do is to plug this in to calculate the volume. The volume in respect to time is 3 times A, which is 0.7 squared, and then times negative 0.1 for the change of a, I want to say area, it's not area, it's length of the side. These are numbers, you can just deal with this stuff, right? This is 0.049, so 3 times 0.049, and then times negative 0.01. I mean negative 0.1. You see that dv dt works out to be a negative number, right? There's only one negative here, nothing else. So now that would move the decimal point this way, 1, and then times 3. This is roughly 50, so 150, so about 0.3. About 150. I mean negative 0.15. Times 10 to the what exponent? Times 10 to the 4th. Negative 4. It's a small number. Alright, I'll do 147. I was rounding, so I don't have to use calculator because it's all the way there. Because these are all decimals. Oh wait, I have negative 0. This is 3 times 4.9 times 10 to the negative 2, and this is put negative in front. This is just 1 times 10 to the negative 1. So yeah, 12. Yeah, that was it. What was the number? 1.47 times 10 to the negative 4, and then we have inches cubed per hour. Wow. Ice cube problem, and when you have the enough information, you just go and take the time derivative, create what we call mathematical model, right? Math model. And then it's important to know how to read these so for the purposes of units, right? Because this is volume, so it has to be centimeter cube, inches cube, mile cube, whatever. And then time, seconds, minutes, hours, days, months, years. And then over here you have length over time, so meters, inches, or whatever, divided by time, which is minutes, seconds, and whatever else. So if you read those carefully, you should be able to pick that up quickly. Well, this is about half, so maybe we should stop here. And then we have cone, we have cone, ladder problem, the rocket camera problem. So we have 3 or 4. I can't fit all of that in this time. So we'll have to have a part 2 next time. We already covered 2 sections, half of this one. So there will be the revenge of related rates next time. The revenge of related rates, yes.
So, quick question. In all these we've done so far, we've just been given dA over dt. What about when we don't have dA over dt?
Well, you have to have something, because anytime when you have a situation, there is something that you can measure, okay, and there's something that you can calculate because you measured some other things.
Okay.
For instance, do I get to calculate the change in your volume as you're reading or exercising, or no, right? But I can measure other things. I can measure your weight, I can measure your, right? So certain things are measured indirectly by calculating, right? And some things are measured directly. So I can measure the change in side, the length of side, right? I can measure that because I have a ruler that I can put next and say he lost 2 inches in an hour. Okay. If you lose 2 inches in an hour, that's just minus 2 inch per hour. Right. That's what it is. So So there are always stuff that you can measure, and then the rest you calculate.
Okay.
But it's important to have the right geometry to begin with. So we're talking about volume in respect to the length of the side, and then you hit that with derivatives, which is what we have.
Right.
And then you get the, I completely forgot about that. And then you get this formula, and you plug in. Your project problem, one of the project problems will be on related rates. Now, I'm not sure which one I'm going to put there yet. I have a whole bunch of things. So the project is generally about 4 or 5 problems, and you have about 2 months to complete that project and hand it in the day of the final. We talked about it day 1, right?
Right.
Good. It's assigned in the syllabus with whatever 8-9% of your grade, and the best one I'm going to submit for publication. Well, there's that. Let me see this. Yeah, bye.